So take a look at these. There we go. Wiggle, wiggle. So just as a note, question number 1, I hope that's an easy one for you. If I wanted to write the derivative of this, I can call it a variety of things, but please do name your derivatives. Don't just write the rule without calling it something. So if I want to call it y prime, I can say y prime is, in this case, what, 36x to the 8th. You could write 4 times 9 or 9 times 4 if you want to, but although it'll say don't simplify, if it's something as simple simplifying as multiplying 2 numbers together, feel free to do that. Or like subtracting 2 numbers for a new exponent in power rule. You don't have to write the exponent as 9 minus 1 or anything like that. But I do want to call this like y prime equals, instead of just scribbling down 36x to the 8th. So this is on the shorter half of this, meaning we're not going to use chain rule. How could I do, and it'll specifically say that, you won't get credit if you do use chain rule. How could I find the derivative of this number 2 without using chain rule? What could I do? Write it as a power function. What power is the square root of x cubed equivalent to? Yeah, x to the 3/2. So 3/2 power. So I can write just like this, because this is equal to, I'm not taking the derivative yet, it's just the same as x to the 3/2. So if I want to take the derivative of it, now it's in power function form, and we can use power rule. So y prime then for this one would be, what, 3/2 times x to the 1 lower power, so 1/2. There's not going to be anything extremely bizarre. But just looking through the rest of this first column, you can see we've got maybe a coefficient and a natural log expression. So just 2 times 1 over x would be the derivative rule. And you could write it like that, or you could write 2 over x, whatever's easier for you. There's not anything that would involve a lot of simplifying anyway. What about, let's see, 5 to the x? The derivative of 5 to the x with respect to x is, 5 to the x, natural log of 5. Remember these natural log expressions, they get tagged on to logarithmic and exponential derivatives. They're always natural log of a number. It's not of x. What about log base 9 of x? The derivative of that? Yeah, it's got a 1 over. Let's see, and what's in the denominator? Yeah, an x and a natural log of 9. Whatever order you want to put those in, but make sure it's not a 9 and a natural log of x. That's one of the most common mistakes I see just out of hurrying. So it's got a 1 over x and a natural log of 9 factor in the denominator also because it's a log base 9. All right, let's see, cosecant of x. Yeah, cosecant, all the co-functions, when you take their derivatives, they all have negatives involved. Y prime here would be negative cosecant of the same letter, x, times cotangent of x. All right, so let's see. Just looking at this second column quickly, notice there's a couple of inverse trig functions, the first one and the last one. Those can be written either like this, or notice that this would be the same as, if you're more used to looking at it or are more comfortable with seeing it in this form, this is inverse tangent of x. These two mean the same. So, and by the way, in GC, if you're typing them, it'd just be atan. For whatever reason, they programmed it to understand it that way. It's built-in function, though. What is the derivative of arctangent of x with respect to x? Yeah, so 1 over, and it's all positive stuff, 1 plus x squared. If it had been arc cotangent, it'd be the same thing, but with a negative. Negative 1 over 1 plus x squared for arc cotangent. What about number 8 here? 0. Yeah, watch out for things that don't have x's in them. If you're taking a derivative with respect to x and there isn't an x, you have a constant. So whether it's e squared or there's a few others in here, I believe. What other numbered item or items do you see here that are also constant functions? 16 and 17. And there's one more. 14. Yeah, none of those involve a variable. There's a sign of e, which is a constant 2.7 or so. Natural log of 7 and pi 3.14 or so to the 1.5 power. So none of these change as, there's only one variable involved and it's y. And so since y is equal to something that isn't a doesn't involve variables. That means y is a constant. So the derivatives of those three are all 0, just like number 8. Let's see. What about this one? Number 15 looks kind of like a mess, although it also kind of looks like number 2. This can be re-expressed as a power function. Which power function is this the same as? X to the what power? Yeah, negative because it's in the denominator, and I've got x squared and cube rooted down there, if that's a word. So cube root and squared is 2/3 as an exponent, and the negative here is because this expression, this power of x, is in the denominator. So that's just another way to write this y prime. I still have to use power rule. Very easy to forget to do that if you take a while trying to figure out what the power is. Remember that you still have to take a derivative. So we've got a coefficient of negative 2/3 times x to 1 lower power, which would be negative 5/3 or negative 1 2/3. Mixed numbers as exponents is not a typical way to see, but it is true. So, all right, so I'm going to skip the rest of these unless you have a specific one that looks confusing to you. All right, so let's take a look at non-2-point question sort of things then. Some slightly more complex guys. All right. So here's a mess. When you see longer expressions to take the derivatives of, again, it's not that you're always going to run into things that look like this, but just the idea is no matter what function you see, if you're given a closed form function rule, with a couple of short exceptions, which we still are going to learn after your mastery test, you have the ability to find the derivatives of them. The things that we haven't talked about how to find derivatives of yet, by the way, that aren't on your mastery test, if you're curious, are what are called tower functions, which are mentioned in 6.3. It's where I have variables as both the base and the exponent in a function, like x to the x power, or like sine of x to the x cubed power, things like that. Also kind of, I don't know why they'd exist like that, but there's a way to find their derivatives that we will learn later. And other things that involve x's and y's jumbled together, so things that aren't written explicitly y equals a function of x or aren't written in function notation, where like maybe xy squared plus something, maybe they're not even actually functions in the sense of y isn't a function of x or x isn't a function of y, but we should still be able to describe rates of change of one with respect to the other. That uses implicit differentiation. That's also something coming up after your mastery test. So, in any case, when you see something messy like this, regardless of whether you think it seems useful, just make sure, look at it as a whole, kind of say, okay, or think about, if I were plugging in numbers, what would be the last step I do order of operation-wise? And then what happens before that? So in this, I've got a square root of a whole larger expression. So in general, this is a square root function. It's just a square root of a whole other inner function. So take a minute maybe to think about what that means, but if I think of this f of x as being a square root of some other function, this stuff underneath we can refer to as g of x, which g of x isn't simple even on its own. But take a few minutes, see what you can do thinking about how would I find the derivative of this. And we'll go through this step by step, but I want to give you a chance to think about it on your own first. But this is an example of a function that has multiple levels of chain rule, if you want to think of it that way. But I hope that looking at it as a whole, there's nothing completely unfamiliar. Like square root functions, we know how to find the derivatives of those. 7 to the x, if that were on its own, fine, good. Tangent of x, great. Sine of x, perfect. Adding stuff even, that's not too bad. There's also a multiplying stuff, product rule. Okay, we've got product rule. Maybe we haven't done that in a couple days. But all the pieces are things that we know. Now it's just a matter of how do we put all of those together. So, and this one's kind of work from the outside in. So starting with this, overall there's the square root. If you're taking a square root of x and finding its derivative, we have a rule for that. If I have a square root of something else, I get to use chain rule. I get to do same thing as with regular square root of x, only square root of another expression. I'm going to have 1 over 2 times the square root of that same g of x, whatever it is, times chain rule, the derivative of that g of x. Now, I just randomly picked the name g of x. There's no reason you would call that g of x just automatically, but whatever you want to call this stuff underneath. That expression with the sine and the tangent and the 7. All that stuff is g of x. So this is what my derivative rule is going to look like overall. G of x, I know. G of x I've just kind of assigned to that. So the only part out of all of this that is yet to be worked out then, so I could write this with the actual 7 to the x times tangent of x plus sine of x in that spot. What I need to do is figure out what's g prime of x, if g of x is the expression that's underneath here. So at this point, you can step back. Okay, we can ignore the square root. We're just trying to work on the derivative of the stuff underneath the square root. And overall, that's just an addition of 2 terms. Second one is really easy to find the derivative of. What's the derivative of sine of x is cosine of x. So we just have to think about what's the derivative of the first part of what's underneath that square root sign. And that's product rule, as we said. So a little messier than just sums and differences, but if g of x is this expression here, then its derivative involves a product rule because of this first part, derivative of sine of x and the derivative of this product, which is a little bit messy, but I hope all those component pieces look familiar. Meaning the derivative of this 7 to the x tangent of x term underneath the square root sign is what I have in parentheses here. The original 7 to the x and the derivative of tangent of x plus original tangent of x and the derivative of 7 to the x. So that's our product rule. I don't want to use f prime g or anything because we already have f's and g's here. But if you want to assign names to these, like call this h of x times k of x, or something like that, then this is h of x times k prime of x, and k of x times h prime of x. That's our product rule. Put the plus in there. And then there's just that plus cosine of x tagged on the end. That's the easy part. That's from the second term here. By the way, in terms of dealing with long and unwieldy functions as a technique for not losing track of what you're supposed to be doing, we'll do a few more like this, but this might be something you want to think about, like write it kind of in general, like square root of, instead of trying to go straight from the problem to the answer all at once, think about the overall structure, say, okay, this is a square root of something, and actually give that something a name so that you can, like off on the side, do some scratch work, name it for yourself, and then substitute back in later. What I mean by substituting back in is, if I want to write out this f prime of x, I know it's going to look like what's right above here. It's just that g prime of x is fairly long. It's all of this stuff. And then g of x is going to be, well, take up a little bit more space than the symbol g of x does. But that way you don't accidentally put a derivative in a spot where the original was supposed to be, or vice versa. If you just write the general structure in terms of made up things, like whether it's a star or a smiley face or a name like g of x, something that you can call it to refer to a whole inner portion of something involving chain rule. because when you write the whole thing out, it looks like a bit of a mess. And you could do this in multiple steps. You could jump straight from here to there with no scratch work in between. By the way, there's not like you get points off if you don't show scratch work on the mastery test or anything like that. No, we just need to see what the final answer is. Whatever steps you use to get there, great. If you didn't use any written down steps, that's fine. Just make sure you write clearly. But again, this is the derivative of everything underneath the square root sign, which involved a product and a sum, times the derivative of square root type things, 1 over 2 times the square root of. And so again, this is why it's maybe useful to have that square root derivative learned separately, even though it really is just a 1/2 power. You could do this just using converting this into that sum all raised to the 1/2 power, and then use power rule also. But if you see, square roots show up a lot in reality, so if you just remember square roots derivatives as their own thing, it makes a quick end to this process. Alright, so there's our lovely expression for our derivative here. Here's another one, a different longish function to find a derivative for. But again, just a lot of things to be intimidated by, but if you break it down, any individual piece of this should look familiar. But step back and think about what's the overall structure of this, or like order of operations wise last, what would you do? If there's a lot of stuff going on, there's usually chain rule involved somewhere. But this one, it's not the outermost part. Actually, I don't, yeah. This one we generally have overall a product of this 9th power expression here times e raised to a power. So here I just picked some other random letters, P and W. But f of x is a product of 2 pieces. Whatever you want to call them. I wouldn't call them f and g since f is already the name of the whole thing. But take a few minutes, see what you can do with this. And then we'll go through it step by step. What I want you to do is feel comfortable that you have a strategy to attack weird-looking function rules. Find their derivatives. Don't attack them. That wouldn't help. So yeah, overall we have a product. So our final answer is going to have a product rule structure to it overall, where I have named these without really declaring it, but named this first part. Let me change a different color other than brown. This first part, and it doesn't really actually matter, calling this P of x, and the second part W of x. No particular meaning to those letters, just something different. So if I see those 2 pieces, I know if I can take the derivatives of each of those separately, I can piece them together with the original factors the way product rule works. One factor times the other factor's derivative plus same thing but the other way around. And since it is all multiplication and addition, it doesn't really matter the order that you do either of those things in. Just make sure that you're not pairing up a function with its own derivative through multiplication. So from here then, like, okay, P of x looks a bit like a mess. W of x looks simpler, but both of them involve chain rule. So if this were just e to the x, that would be great. E to the x is its own derivative. Yay, we're done. It's not. It's e to the something else. I have an inner function here. I've got something whose derivative I'm going to have to take when I'm taking w of x's derivative as a whole. It's exponential in form, though. P of x is a power function. It's a ninth power, but of some other power functions, or, well, of not a binomial because it's got a fractional exponent, but of a two-term power function expression. Two power functions subtracted, I suppose I should say. So either one on their own don't look too bad, but neither is extremely simple either. So what about, there we go, p prime of x, the first part? Since I have a ninth power expression, my derivative is going to involve 9 times that same expression to the 8th. So that's our power rule of the ninth power. And then we've got this inner function whose derivative we haven't taken. Now, I just wanted to point out one of the common errors I see with chain rule, is this being stubborn, that pertains to, pertains to power rule and chain rule. Often what I see instead of something like this is this derivative inside here to the 8th power. So make sure when you're doing derivatives, if you're taking a derivative of something like x to the 9th power, by the time you're done it's 9x to the 8th. It's still x that's the base of the power. The base of the power doesn't change, only the exponent changes. So when I have this two-term expression raised to the 9th, by the time I'm taking the derivative, I should have that same exact two-term expression raised to the 8th, not its derivative raised to the 8th. The derivative of this inner function isn't going to be raised to any power. So this derivative is just tacked on as a separate factor. The derivative of x to the 3/4 power involves power rule, 3/4 x to the 1 lower power, negative 1/4, and then minus the derivative of 5x, so maybe that's easier, minus 5. Sometimes the easy ones, you second guess yourself because it looks so short or it looks strange. It's missing some difficulty levels. But in any case then, our derivative for the power function part, the first listed of the two factors here, should look like that. Two big chunks multiplied together using quotient chain rule. And then e to the 6x, or 6 square root of x power. If it was e to the 6x power, that'd be easier. E to the 6x times 6, the derivative of the exponent. But this derivative of the exponent is, well, a little messier. So didn't write out all the steps of chain rule, but e to the something power, whatever's up here, is going to have its whole original self in its derivative. And this is times the derivative of the exponent is what this is. The derivative of 6 times the square root of x is the derivative of this. The 6 over 2 times the square root of x. The 1 over 2 root x would be square root of x with an extra 6 in front. You could write it like this. You could write it 6 times 1 over 2 root x. Those are equivalent. If you don't have to combine the coefficient constant multiple in with that if you don't want to. But in any case, this w prime of x involves derivative of 6 to the square root of x and the derivative of an exponential function, which is essentially just itself. This is e, so there isn't any extra times natural log of e that you have to tag on because that equals 1. So continuing on here, if I want to put these together, I have all the component pieces that I need. The overall function f here was a product of 2 pieces. Each piece I've found the derivative of separately. I need to put them back together using product rule, which would look like a mess, but just follow your order. And if you tend to forget product rule in the middle of doing something else, write it down for yourself. Any rules that you tend to forget, whether it's just like arctangents rule or quotient rule, whatever it is, when you get your mastery test, feel free to just jot those down on there as notes to yourself to use later so that you can focus on the question at hand and not be afraid that you're going to forget something that is the most challenging part for you to remember of those other pieces. But product rule would look like this then. So putting in our pieces looks like an awful mess, but reading carefully, we can see we've just got, here's this first piece here. This is our x to the 3/4 minus 5x to the 9. So that's the original first factor times the derivative of the second. Oops, ends there. Plus, other way around, the original second factor and the derivative of the first factor from f of x. So it's got all the pieces, just by the time you write it out, it takes a lot of space. So don't look at the end and then try to go back and like, oh my gosh, that's horrible. Start at the beginning. We've got a product. And we find the derivative of a product by using this product rule format where we do each of the pieces individually. Nick? No, I just put in some extra brackets and parentheses to clarify here, but yeah, there's a lot of excess ones, like those brackets there, that's all a monomial inside, so I don't, or whatever, it's a one-term expression, there's no addition or subtraction, so that would all get multiplied on. Also, these brackets are not required because it's inside. I've got these parentheses that contain the subtraction, and there's just multiplication. So there's just, I put excess things in there for emphasis, just to emphasize which pieces came from where. But yeah, if you have extra, it never hurts, but make sure you do have parentheses or brackets if you're using them where needed to group addition or subtraction together. That's all supposed to be multiplied onto or divided by something else. All right, one more, maybe. Oh, sorry. There we go. Quotients are usually the easiest to identify. Overall, we've got a quotient. But there's a lot of other stuff in it. So I'll let you think about this one. So we've got a quotient, which means that we want to use quotient rule. So whatever letters you picked, I did A and B. The derivative of a quotient involves a quotient, where the numerator is kind of like product rule, but with a subtraction. And the first half of the numerator has the derivative of the original numerator expression times the original denominator minus original numerator times derivative of denominator, all over denominator squared. Derived from product rule with chain rule, actually, is what goes on with that. But with our numerator of log base 2 of 4x, this does simplify, by the way, but you certainly don't need to simplify it. If you can see, there's a factor of 4 in the denominator and a times 4. But log base 2 of something is, log base 2 of x is 1 over x times the natural log of 2. Log base 2 of something else is going to be 1 over that something else, 4x, times the natural log of 2. But this inner function here has its own derivative. It's just a 4, but don't forget about it. So 1 over that times the natural log of 2 times the derivative of that expression circled. That's where this 4 comes from. So in any case, there's our derivative of the numerator. Denominator, we just did something kind of similar to this. We had an e to the 6 root x. Here we just have a 3 to a regular square root of x. So derivative of 3 to a power is 3 to a power, same exact power, times the derivative of that power and also times the natural log of 3. So this just comes from, like 3 to the x would have that same natural log of 3 factor in there. 3 to the anything variable power is going to have natural log of 3 and as a part of its derivative. Here's the derivative of the exponent, square root of x. And then you can write this a couple of different ways. The derivative of cosecant of x is negative cosecant cotangent, both of x. So if I have subtracting cosecant of x, this is our subtracting a negative. So you could also have minus negative cosecant of x, cotangent of x. Don't forget the x's in there. It's really easy when you're studying to say kind of like how I just said that, oh, cosecant, cotangent, just kind of to keep the trig functions in mind. Whatever the variable is, you do need it after each of those functions in there. And by the way, if it's something more than just an x, that something more than just an x translates into each of the pieces also. So you could write plus or minus a negative, either one obviously. Those are equivalent, but we have all the component pieces. They're just all a mess at this point. We want to put these together. We've got the derivative of the numerator, the derivative of the denominator. So putting those together in quotient rule takes up a bit of space. But I don't know if you can see that from where you are. That's the largest I could get it to show up and not fall off the bottom of the page. So that's a messy one, but it's just all the pieces we have put together. And don't worry about simplifying compound fractions or anything like that either. Just got the derivative of the original numerator expression times the denominator as it was, minus, here's the minus of the numerator of quotient rule, minus the original denominator, or the original numerator rather, and the derivative of the denominator is this expression in parentheses, all over original denominator squared. Aside from the numerator in quotient rule being something that people accidentally get in the wrong order, most common other mistake I see with quotient rule is you get so busy with putting together the numerator because it's a big mess that you forget about the denominator by the time you're done and just don't write it as if it was product rule. So make sure you don't forget the denominator of quotient rule when you're writing it. All right, so next week we'll do a couple questions at the start of class on Monday, but I hope that after maybe seeing these, you'll have more confidence to try some challenging problems over the weekend for review. So we're not done yet, but just let me tell you what I'm going to have you do over the weekend. We are going to talk about other stuff. We've still got 15 minutes. But over the weekend, in addition to working on the iMath AS derivative practice online, you also have your 150 derivatives that you got in recitation a long time ago that they're going to be turning in here on Monday. I'm going to post an additional 40 or so questions, not all this hard, but medium to hard. They're not going to be like 2 to the x. So that you have practice at those additional ones. Just for something else, extra challenge if you want. Or something else, oh, and some reading. But in any case, for over the weekend, I will give you some additional medium to difficult problems to work on so that you can build up your confidence before whatever it is you're going to take the hard portion of the test. I hope that the easy portion on Wednesday is easy. But what I did want to talk about for the rest of today was yeah, so the extra problems, if you want to talk about those, you can come and stop by office hours or something like that. But yeah, they're just kind of for you extra independent study. They're not to be turned in. So I appended kind of to the bottom of your last homework assignment, thinking about some things that we talked about earlier. Now that we've talked about derivatives a lot in their closed form, we're going to deal more with some topics we talked about earlier. We talked about rate of change just as a general premise and just called things R sub f and maybe didn't have a formula associated with it, a function rule. Or maybe we started with a function rule for rate of change and didn't do anything with it other than just kind of write it. We're going to be doing some more things now that we know how to go from an accumulation function to a rate of change function in closed form pretty quickly. But I don't want you to forget about all the meanings of these things. So we're going to talk about recapping some of the meanings and some additional things we can discuss with this. And also the, like writing accumulation using integrals. We'll get back to doing that again. We just took a side trip in to learn a bunch of rules. But take a look at this. So I've got a tangent line in green, if you can see that, but kind of flowing along this. Just the red graph on the right, this is a graph of f of x. So let me just write on this here. So this is a curve y equals f of x, this red curve here. And this green isn't anything. It approximates f of x as it scoots along. The green line is a linear function, but it's changing all the time. So if you can see what's going on over here, I've got a rate function, r of x, which is the derivative of f of x. Oh, let me just, there's n's in here from the automatic slider. Let me just, I think I have a white. Let me cover these over. All right. X and r of x. There we go. So as this scoots along, I can see, if I'm thinking of this as my accumulation function, f of x, of something, you can think of it as maybe it's temperature that was negative and then positive and then goes back to negative again, so we're like in Minnesota in the winter, or whatever you want it to be. But this is an accumulation function of some sort. If you start at 0, you might even think it's, oh, it's net accumulation starting at 0 or whatever, but think of it as some sort of accumulation. And this green line is a tangent line to that, meaning it's approximating the accumulation as we go along in such a way that its rate of change is the same as x progresses, or as x varies through this. So let me just pause this for a minute because it's kind of distracting to have things wiggling. Maybe. There we go. So taking a look at this red graph, this is things we talked about before, but I should be able to see intervals where the red graph of accumulation is increasing or where it's decreasing. So where's the accumulation? Where's this red graph's dependent value? Let's see what would be the easiest to answer in here. Where does it change someplace from increasing to decreasing or vice versa? What's one x value where it changes? You see an x value where it can where this is kind of changing from increasing to decreasing? Let's see. So this is an accumulation graph. So this is, our amount is up here, and maybe imagine like this is temperature, and this is time measured in whatever units you want it to be measured in, but not a rate graph, but this is just an accumulation of temperature. So temperature started out low and was increasing or decreasing here. As I go from left to right, is temperature increasing or decreasing if this is a graph of temperature? It's increasing. These are negative temperatures, but it's as I go forward in time, my temperature is going from -10 up to 0, and it keeps increasing until I get to about there, right? So this is just, we've looked at all sorts of different graphs. This one is just a graph of an amount. In this case, it's a temperature or an accumulation of things, however you want to think of this. But from the beginning of this graph that we can see, negative 3.5 through about here. Let's see, maybe that's negative 1.8 or so. On that interval, f of x increases, or the temperature increases. And then it decreases for a while, right? My temperature decreases from this negative 1.8. It keeps decreasing until I get to about here, 1.1. So from about negative 1.8 through positive 1.1, and this isn't a coordinate, these aren't coordinate pairs, these are intervals of x. We've got, well, I guess I shouldn't say f of, yeah, it does. F of x is decreasing. The y values are decreasing. These are graphs of f of x. And then it starts increasing again until the end of this, which is about 1.5. So I'll just use that. So from 1.1 through 1.5, f of x is increasing again. So from left to right, I've got graph going uphill and then downhill and then uphill a little bit at the end. If you're looking at a graph of accumulation, increasing versus decreasing is just that goes uphill, goes downhill. When you're looking at a Cartesian graph, if you're looking at a polar graph, it goes out and goes in. We're not going to deal with those a lot, but you will in calculus too. In any case, so just make sure you're careful what sort of graph you're looking at. If I say that this is a graph of an accumulation, I can see that f of x, the dependent values are increasing if as I go from left to right, or as x varies to get larger, my y values go up, get larger also. So thinking about the rate, r of x, the derivative of f of x. So the rate of change of this graph, or the derivative of f of x, if f of x is increasing, what does that tell me about its rate of change, about f of x's rate of change? If a function is increasing, what's true about its rate of change? Positive, right? We talked about this before. This is on your test too. So when I say here that f of x is increasing, or f of x increases, however I wrote it, that also means that its rate of change function, r, or r sub f, I just didn't use subscripts here because it's messy, r sub f of x is positive. And if f of x is decreasing, that tells me that r sub f is negative, right? And again, this increases would be r sub f is positive on these same exact intervals, positive. So when f of x, when a function is increasing, its rate of change is positive. So you could say that the other way around also. If you saw in a graph, and we've seen these before, a rate of change graph, and I ask you what's happening with the accumulation, if you saw a rate of change that was positive, you know that whatever is accumulating is positively accumulating or growing. If you have a rate that's negative, you have accumulation actually decreasing. You talk about deaccumulation, or the dependent variable of the accumulation function is shrinking in value. So I can talk about these intervals, which, again, just from negative 3.5, where we can see up through this negative 1.8, and then negative 1.8 through 1.1, and 1.1 to 1.5. Those different intervals I've got, I'm pointing at the screen, that doesn't make any sense. This section I've got f of x increasing, r sub f of x positive. The next interval I've got f of x decreasing, r sub f of x negative. And then, again, the positives and increasing in the last little section there. So while r sub f of x is positive in this first section here, r sub f of x is positive from the left end of the graph to here. Is it a constant value? Is r sub f of x constant between negative 3.5 and negative 1.8? Is it the same constant positive value? We know it's positive, but is it one value or multiple values? Multiple values. So what's happening to those? Is it, let's see, is it larger at the beginning or the end of that interval? That's a positive value. Yeah, at the beginning I've got larger positive rates, and at the end of this interval I've got, well, essentially 0 rates. If you notice from this list of intervals here, I use all open intervals. At negative 1.8, I wouldn't say that the graph is either increasing or decreasing. It's changing over from one to the other. In this immediate vicinity, I could say that the rate of change of f of x is essentially 0, and the closer I get to that peak of the hill, the closer that rate is going to be to 0. But I can't have rates of, like, I can't have no motion, so I can't really have, like, over an interval here that's of any width. It's not going to stay 0 because this isn't a flat curve like that. But the smaller my moments get right to wherever the peak of this hill is, and I just estimated it's at 1.8, the closer the rates become in that area to being essentially 0. So r sub f of x, when x is about, whatever this is, negative 1.8, it's approximately 0. So it's going from increasing, but increasing very slowly, to decreasing, but decreasing very slowly. So let's talk about next time. What are the patterns in the values of the rate? We said the rate is very positive here and turns to 0 there. What we're going to talk about next time is, what if my rate is increasing, or if my rate is decreasing? What can I do with that information? Because we've talked about rates being positive or negative, and original functions being increasing or decreasing. But what if I talk about my rate increasing or decreasing? What additional information does that give me? Or how is that related to anything else we've talked about? So that's next time, in addition to a few mastery practice questions on Monday. All right, but that is it for today. Study well. I believe Cerny is here looking for, let's see. All right, perfect.